Okay, in today's lesson, we're going to be looking again at acid-base titrations. We've already looked at acid-base titrations in grade 11, and we're going to need those skills that we learned in grade 11 in order to study acid-base titrations here in grade 12. But then once we've reminded ourselves of those skills, we will use them to analyze a titration in more detail than in grade 11. In grade 11, we were only worried about when the color change took place. All right, let's just do a quick review of this. You should have been given the notes for this on a handout. And in grade 11, we learned that the powerful nature of a titration is able to determine the concentration of an unknown solution by making the moles of acid equal to the moles of base. We call that the equivalence point. All right. So equivalence point means that we have the same moles of acid as we have the moles of base. And that's a very important concept, right? We're going to be using that in obviously this year's analysis of titrations as well. We also know from last year that there is an end point in a titration, and that's the point at which the color changes for the indicator, all right? So they're actually two separate things. An indicator actually has to be chosen so that it changes color at the right time, okay? Because sometimes we can have the moles of acid equal to the moles of base, but it may not take place at the same pH as, say, the end point, all right? We're going to learn this year that not all equivalence points take place at a pH of 7, all right? Because in the past, we've just assumed if we've got the same moles of acid as we do moles of base, then it should be completely neutralized, and therefore we should have a pH of 7. But that is not necessarily the case, all right? It depends on whether we're titrating a strong acid with a strong base or a weak acid with a strong base or any other combination, right? We could talk about a strong acid and a weak base, all right? So the equivalence point is where the moles are the same, and in the end, we want an indicator to change color so that we know when the equivalence point takes place, all right? That color change is what we call the end point, and in an ideal world, the pH of the end point needs to be equal to the pH of the equivalence point. So before we continue on here, let's talk a little bit about indicators. Now, in the past, we haven't worried too much about the indicators, but an indicator is actually a weak acid, or it could be a weak base, depending on what type of molecule it is. And we'll represent that weak acid as being H with an IN, and IN is representing indicator. And if we put some indicator into a solution, then that indicator molecule will react with water just like any weak acid, produce some H3O+, and then produce a base form of the indicator. And this acid form and this base form would have different colors, all right? If I was talking perhaps maybe about bromethymol blue, we just used bromethymol blue in our KSP experiment. And in the acid, when we titrated with acid, that bromethymol blue was yellow, right? And in the base, that bromethymol blue was blue. Okay? And if we add an external source of acid, let's say we've got lots of acid in our solution to begin with, and we add the indicator, that excess acid increases the amount of H3O+, and according to Le Chatelier's principle, that will push the equilibrium over to the left, and that will make the solution more yellow, all right? If we add base to this particular situation, I'll use a different color to illustrate this. If I add base to this particular indicator, that's going to consume the H3O+. That's going to bring the concentration of the H3O+, it's going to bring it down. Due to Le Chatelier's principle, it will shift right, and it will cause the solution to become blue, all right? Now, right at the balance point between the acid form and the base form, where we have equal amounts of the acid form and equal amounts of the base form, we will have that intermediate color. And in this case, it's simply yellow and blue put together, and we have green in the middle, all right? Now, all indicators will have a particular pH where this intermediate color takes place, or where this change takes place, and that's due to the Ka of the indicator. Maybe I should call it K indicator, all right? And we're not going to go into great details about the Ks for each indicator molecule, but in university you will. You'll talk about the Ks for the indicator molecules. But for our class here, I am simply going to supply you with a table like this, and this table gives you an indication on where the color change takes place. All right. So let's take a look at some of these examples here. So where's my bromethymol blue? Let's see if we can find it. Bromethymol blue. Oh, it's near the middle. I'm searching. Right here. Bromethymol blue. Right here in the second column. Color of the acid form, right? So color of the acid form, yellow. Color of the base form, blue. And it turns out that bromethymol blue changes color in between 6.2 and 7.6. So it has a K value such that its perfect balance point, where the concentration of the acid version and the concentration of the base version are equal, takes place at 6.2 and 7.6. That's nice. That's right up in the middle. That's right about where 7 is. So we got a pH of 7 nicely there in the middle. Let's take a look at some other indicators that we've used before. Here's good old phenolphthalein. We've used that many times. We used it the other day to determine the Ka for acetic acid. And you'll notice, again, the indicator acid color is colorless. The base color is red, or fuchsia, or magenta, or whatever you want to call it. But notice the pH range where that changes color. 9 is in the middle. So phenolphthalein actually goes from colorless to red, or to magenta, at a pH of 9. So its K value is different than bromethymol blue's K value. All right? And so you can see that there's all kinds of different indicators, and depending on what you're titrating, and depending on where you want the color change, over here, if I look at this methyl violet right here, its color change happens way down at a highly acidic range, 0 to 1.6. It's changing color right away. And if we take a look here at the top end here, 1,3,5-trinitrobenzene right there, it changes color between 12 and 14. You may have used something called the universal indicator that changes color all the way through from acidic to base, and that would simply be a mixture of indicators that then results in color changes all the way along as pH is changing. All right? So indicators have specific pH ranges in which they will change color, and we're going to need to choose an appropriate indicator depending on what we're titrating. All right? And that's really the basics of how an indicator works. That's all you need to know here. You'll learn that there are Ks associated with these things in university. We're not going to deal with that right here. So just as an example, bromethymol blue changes color between 6 and 7.6. Therefore, it's best to use titrations whose end point would occur at a pH of around 6.8, somewhere in the middle. All right? So if we've got the point where the equivalence point, right, takes place at a pH of 6.8, then we're going to want to use bromethymol blue. Phenolphthalein changes between 8.2 and 10, and therefore it's best to use a titration whose equivalence point, this actually should say equivalence point, would occur at 9.1. Actually, that is a significant factor. We should change this. The endpoints are the color change. This is an equivalence point where the moles are the same. Again, where the equivalence point, all right, would be. And the equivalence point is where we have the moles of acid equal to the moles of base. So let's talk about a very simple example of titrating a strong acid with a strong base. And this example is something that I don't think we've done this one before as a titration, but we can make some sense out of it. And so we're going to have some hydrochloric acid and we're going to have some sodium hydroxide reacting together to form some sodium chloride and some water. And if we're talking about at the equivalence point, then that means we would have a certain number of moles of acid and we would have a certain number of moles of base. And at the equivalence point, the number of moles of acid is equal to the number of moles of base. All right? Now, there's no mathematics involved in this particular one because it's not quite as exciting as weak acids and bases, which we will do in the next couple of movies, because I'm going to break this into 3 different movies. But if we have this case, we've got a ratio of 1 to 1 to 1. In the end, this is going to react with this, and in the end, it's going to become all NaOH. We're going to end up with, all NaCl. We're going to have N moles of NaCl. And we're also going to get some water produced, but we're not worried about that water. That water is going off in with the rest of the water in which it's dissolved, and there'll be no necessary effect. So, entities in the water at the equivalence point. All of the HCl at the equivalence point, Na is equal to 0. And that's because all of the acid has been consumed. It's been consumed by the base. So the number of moles of base at the equivalence point is also 0. There is no base molecules left. They've all accepted H's from the HCl. And the next question then is the number of moles of NaCl at the equivalence point. Well, that comes from all of these A's and B's. So it's equal to the moles of A and B that we started with. It's equal to Na. It's also equal to Nb. In other words, it is all NaCl. So at the equivalence point, there's no acid left. There's no base molecules left. There's just sodium chloride molecules. So if I wanted to figure out the pH at the equivalence point, pH, I have to ask myself, what's in the water? Well, there's salt in the water. There's NaCl in the water, and that's going to dissociate. We know how to deal with a salt when it's in the water. We break it into its ions, and then we ask ourselves, what are those ions? Are they acidic ions? Are they basic ions? Or are they neutral ions? And we did this, I believe, 2 lessons ago. All right, 2 lessons ago when we talked about the pH of salt solutions. Well, let's analyze the sodium. Na+. What do we call Na+? Well, it's a spectator ion. It's a spectator ion. Spectator. You know, it's not an acid or a base. It comes from a super weak base, so it's technically it comes from a super strong base, sodium hydroxide, so technically it's a super weak base. It's a spectator. So will it undergo hydrolysis? No hydrolysis. And I got to say it that way, you know, because I can't spell it any other way. All right. So sodium, spectator ions, no hydrolysis. What about the chloride ions? Chloride ions, they come from a very strong acid, HCl, which makes them a super weak conjugate base, right? And if we have a super weak conjugate base, remember, it's also a spectator, all right? It's a super weak conjugate base. And if it's a super weak conjugate base, there is no hydrolysis there. So what's happening in this water? Well, we've got spectator sodiums, we've got spectator chlorides, which means the only exciting thing happening in the water is a couple of H2Os running into each other, right, to produce some H3O plus OH minus. And if there's no external acid or base, then we have a pH of 7. In other words, at the equivalence point, the pH is 7 because the only reaction happening in the water is the natural reaction of H3O plus and OH breaking apart, producing a very small concentration amount of room, but the Kw is equal to 1.0 times 10 to the negative 14, which means the concentration of H3O plus and OH minus is 10 to the negative 7, a pH of 7. That's a neutral solution. It's not very exciting. Let me introduce to you, before we continue on with the next movie, to a term called a titration curve. All right? A titration curve graphs the pH of a solution, the pH of the solution in the Erlenmeyer flask, plotted against the volume of the titrant, the volume of the liquid that's in the burette. Okay? So in our last situation, most cases, we would have, right, HCl in here. So therefore, the pH would be low, right? It would be less than 7, a low pH. And we would add, right, we would add some NaOH to that. And as time goes on, so as we add NaOH, what should happen to the pH? The pH will increase. It'll head up towards 14. So if we were to take that volume added, so as we take our differences, right, as the volume is added, and we plot that versus the pH of this solution, we'll get what is called a titration curve. Let's take a look at example titration curve. You have this on your sheet that you've been handed, so you don't need to draw it out. And this is a strong, what do we got? A strong acid and a strong base. And if we had our acid in the Erlenmeyer flask, that pH probe, if we're doing this with a computer, is going to start out nice and low down here. And we will see when we do an experiment that the pH actually starts off changing very slowly. I'm going to change the color here. Changing very slowly until we get very close to the equivalence point. Once we get very close to the equivalence point, the pH starts to dramatically increase, all right? And it's the steepest at the equivalence point. We have the steepest change. Now remember, pH is a logarithmic scale, which means we are dealing with powers of 10 when we're graphing this pH. So as we get close to the equivalence point, and as the acid is being consumed, every drop of base that we add, every little drop of base causes a large change in the pH as we get close to the equivalence point, because every drop is going to change that concentration of the HCl by a large factor as the HCl is all being consumed. It's being consumed, and every drop now is really changing that H3O plus concentration by large amounts, and so it shoots up, all right? Now this is what makes titration so powerful as a measuring technique. Because one drop, right, this swing up here can happen in one single drop, because one drop can cause an upswing in pH so great, our indicator color will change drastically. So right here, this is where we want the indicator, right, to change color. In other words, we want that to be the end point. Okay? And that's spelled wrong, the end point. All right. So if we take a look at a strong acid and strong base, we've already concluded sodium chloride is going to be in the water at the equivalence point. That means the pH is going to be exactly 7. The pH at the equivalence point is 7, which means we're going to want to have an indicator that will change color between 6 and 7. And so if we could get some litmus in a liquid form, and you could get litmus in a liquid form, we could use litmus to indicate that pH of 7 change, and that would tell us when we have the same number of moles of acid and the same number of moles of base. All right? So there's an introduction to how indicators work, also an introduction to titration curves. And I'm going to break this video into 3 little ones. The next video will talk about what happens when we titrate, and now I'm going to cheat ahead, when we titrate a weak acid and a strong base. All right? So we'll take a look at that in a moment.